Welcome, ninth graders, to today's Explainer. We are going to build out your ultimate geometry toolkit for understanding the hidden properties of circles. Believe it or not, circles absolutely govern the mechanics of the world around us. We're talking everything from the orbit of satellites in space down to the exact distance you can see toward the horizon on a clear day. And today, we're going to unlock the mathematical secrets behind these shapes.
Here is our roadmap for the next 10 minutes or so. First, we'll set our explainer objective. Then, we'll define tangents and inscribed angles, followed by the Chords and Secants product theorems. After that, we've got a really cool worked example calculating an airplane's distance to the horizon. We'll do a quick misconception and formative check, and finally, wrap it all up with a required concepts recap.
All right, section 1. Let's jump straight into our explainer objective and start mastering this geometry toolkit.
By the end of our time together today, you are going to completely master 4 incredibly specific, powerful geometric concepts: chords, secants, tangents, and inscribed angles. And I promise you, these aren't just random vocabulary words to memorize for a test. They're actual structural keys. Once you understand exactly how these lines and angles behave both inside and outside of a circle, you'll be able to solve some seriously complex spatial problems with just a few simple calculations.
Moving right along to section 2, let's start defining our first two terms, tangents and inscribed angles.
So, what is a tangent? Well, it's a pretty unique line because it touches the edge of a circle at exactly one single point. Think about a bicycle tire resting on flat pavement. That flat ground is perfectly tangent to the tire. Now here's where it gets really powerful. It's called the tangent radius property. At that exact point of connection, if you draw a line straight to the center of the circle, which is your radius, it creates a perfectly perpendicular 90-degree intersection. That 90-degree angle is a massive advantage for us because it means we can instantly create right triangles, totally unlocking the Pythagorean theorem for circles.
Next up, we have the inscribed angle. Now, unlike a central angle that anchors right in the middle of the circle, an inscribed angle has its vertex sitting directly on the outer edge of the circle itself. And from that point on the edge, its two rays stretch all the way across the inside of the circle, hitting two other points. Those rays are actually called chords. So basically, you've got this angle wedged right into the outer curve of the circle, looking inward.
Here is the absolute golden rule for these. The measure of an inscribed angle is always exactly half the measure of the arc it intercepts. So picture those two rays stretching out, it essentially capturing a piece of the circle's curved edge. That captured piece is your intercepted arc. If you know the degree measure of that arc, all you have to do is chop it in half and boom, you have the exact measure of your inscribed angle. It's a perfectly consistent 2-to-1 ratio every single time.
This actually perfectly illustrates Thales' theorem, which is a brilliant, direct result of what we just talked about. Think about it like this. A full circle is 360 degrees, right? So a semicircle, which is exactly half, is 180 degrees. If your inscribed angle stretches its rays all the way across to capture a 180-degree semicircle, the angle itself has to be exactly half of that. And half of 180 is 90. So any angle inscribed in a semicircle is mathematically guaranteed to be a perfect 90-degree right angle. Pretty cool, right?
Okay, on to section 3. Let's look at the Chords and Secants product theorems, which explore what happens when these lines actually intersect. Imagine you have two chords, which, remember, are line segments whose endpoints stay strictly on the circle, intersecting on the inside. Let's say chord AB and chord CD cross each other at a random point inside, which we'll call point P. When they cross, they slice each other into smaller segments. The chord-chord product theorem tells us that the product of the segment lengths of one chord will exactly equal the product of the segment lengths of the other. Simply put, if you multiply the length of part AP by part PB, you will get the exact same number as when you multiply part CP by part PD. It's this gorgeous, perfect internal balance.
Now, let's completely flip the scenario. Picture a point sitting completely outside the circle. Let's call it point P again. From this external point, we draw two lines. One is a secant line, meaning it cuts straight through the circle, intersecting it twice. The other is a tangent line, which, as we know, just barely grazes the edge of the circle at one specific point. Because these lines meet at that shared outside point, a very strict mathematical rule kicks in, known as the tangent-secant product theorem. It tells us that if you square the length of the tangent segment, it will perfectly equal the total length of the secant multiplied by just its external part. So grab the entire length of the secant from the outside point all the way to the far edge of the circle and multiply it by just the piece that's hanging out in the empty space outside. That product will always equal your tangent squared.
All right, section 4.
It's time to shift from pure theory to application. Let's tackle a worked example featuring an airplane and the horizon. Real-world geometry in action.
Picture a passenger sitting in a window seat on a flight cruising at an altitude of 9 kilometers. She looks out and wonders, exactly how far away is the horizon line right now? Well, we can actually calculate this exact distance in 3 simple steps, just by using the tangent radius property we covered earlier.
Let's pull our data together. The Earth's radius is roughly 6,400 kilometers. Our airplane is sitting 9 kilometers above the surface. Because the sight line from the airplane grazing the visible horizon acts as a perfect tangent line, it is perfectly perpendicular to the Earth's radius right at that visual edge. This sets up a massive right triangle right there in the sky. The Earth's radius to the horizon is one leg, coming in at 6,400 kilometers. The sight line to the horizon is our unknown, let's call it x, and our hypotenuse, that's the distance from the center of the Earth straight up to the plane. So we add the 6,400 kilometer radius to the 9 kilometer altitude, giving us a hypotenuse of 6,409 kilometers.
Now we just deploy the Pythagorean theorem. So x squared plus 6,400 squared equals 6,409 squared. When we crunch those numbers, x squared equals exactly 115,281. Take the square root of that, and we find our tangent distance is roughly 340 kilometers. Our passenger is looking at a horizon line that is 340 kilometers away, and we proved it completely using basic circle geometry.
Let's move on to Section 5. We're going to clear up a common mental trap and do a quick, formative check to test your knowledge.
So a really frequent mistake in geometry is confusing chords and secants. It happens a lot because they both involve crossing through a circle. But precision here is everything. Always remember, chords strictly stop at the circle's edge. Their endpoints are permanently anchored on the circle itself. Secants, however, intersect the circle but then boldly extend outside of it, continuing into the surrounding space. A secant is a continuous line. A chord is a contained segment.
All right, let's test your active recall with a quick question. Based on what we established earlier about intercepted arcs, think about this. If an inscribed angle's intercepted arc is exactly 112 degrees, what is the measure of the angle itself? Take a quick second to lock in your answer.
Did you get it? It is exactly 56 degrees, because that inscribed angle is mathematically always half the measure of the intercepted arc. You just take your 112, divide it by 2, and you're good to go.
Finally, we've made it to Section 6. Let's do a rapid-fire recap of our required concepts to really solidify your geometry toolkit.
We have covered some serious ground today. We established that the perpendicular tangent radius property effortlessly creates 90-degree angles for us. We learned the inscribed angle theorem, which guarantees that cool 1-to-2 relationship with its intercepted arc. And we unlocked those incredibly useful product theorems for both intersecting chords inside the circle and secants and tangents meeting out at an external point.
To wrap things up, I want to leave you with a thought. We just calculated the exact distance to the literal horizon using nothing but a tangent line and a radius. Next time you're looking out a window or at a satellite dish or really anything curved, ask yourself, what other massive real-world measurements and hidden distances could you unlock if you simply knew where the tangent lines were? The world is absolutely full of hidden right triangles, just waiting for you to draw them in.